Hello everyone, let us start lecture 13. In our previous lectures, we have come across this triangle where RT ln k equal to NF E0, delta Z0 equal to minus NF E0 and delta Z0 equal to minus RT ln k. At the same time, we have come across this Nernst equation where E ox rad equal to E0 ox rad plus RT NF ln activity of ox, activity of rad for this reaction ox plus Ne equal to rad. So, this is the Nernst equation what we have for reduction. At the same time, this activity part can be written in terms of molar concentration ox rad when we consider dilute solution and also the ideality. Means activity equal to activity coefficient, this is the activity coefficient and this is the concentration in molar concentration. Now, this activity coefficient will be 1 when we considered very dilute solution where ideality is maintained. That time I can write this. Now, this particular is called standard reduction potential. And when we achieve the standard reduction potential, which is 25 degrees Celsius, 1 atmosphere pressure and activity of ox, activity of rad equal to 1, that time we get this equal to rad. Now, once we have this particular knowledge, then also we have looked at this hydrogen evolution as well as, and we saw that both these reactions, both these reduction reactions are basically same reaction. Only thing is in the Nernst equation in case of N, in this case N equal to 1, in this case N equal to 2, but finally we would come across this would be equal to E H plus half H 2 plus R T F ln activity of H plus and P H 2 half would be equal to E and you would see that both the cases the equations would remain same. Now, also we have tried to find out the value of this, and for example, for this reaction we get delta Z0 equal to mu 0 H H2 half minus mu 0 H plus, since we are considering half, and then from that this is considered, this is the as per convention, this is 0, this is also 0 in standard state, then we would get 0. So, delta 0 0 equal to 0 equal to minus n equal to 1 f E 0. So, E 0 becomes 0. Similarly, you would get the same value E 0 equal to 0. This is what we have learned from our previous lectures. Now, let us see whether this we can find out E 0 for other reduction process, and initially we would consider pure element and pure element ions of pure element. That means, in a particular solution we have the ions of that particular atom, that particular element, and that element is getting, that ions are getting reduced. So, now for example, if I consider Ni plus 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 2E equal to Ni, this reduction process if you consider, we consider the reduction of ions of pure element and then try to find out E 0 m n plus m. So, that means the reaction would be n plus Ne equal to m. So, m is equal to, m is nothing but pure element. Now, if I consider this, we can also find out E 0 for this process. Now, mu Ni plus plus 0, it has a value of minus 48250 joule per mole, whereas mu 0 at standard state, that means 25 degrees Celsius, 1 atmosphere and solid, as we have said that in case of solid, if it is pure and the stable state in this at this particular conditions, we have to consider, for example, oxygen at this temperature 1 atmosphere, it is gas. So, it is a stable form, that is what the mu 0 of oxygen gas would be 0. Here also this is solid nickel, which is the stable condition at 25 degrees Celsius and 1 atmosphere pressure. So, then also it is assigned as 0. So, now we can find out delta Z 0 equal to mu 0 Ni minus mu 0 Ni plus plus, then it becomes plus 48250, which is nothing but minus 2 F E 0 Ni plus plus Ni. Remember, since we are considering reduction process, that is what we are writing the reduction free energy change, the nickel from this reaction. So, once we have this, then we can find out E 0 equal to plus plus Ni equal to 48 minus 250 by 2 into 96500 F, which is the 1 Faraday, which is nothing but 96,500 coulomb. So, you know how we get it. It is basically charge of Avogadro number of electrons. So, if you multiply Avogadro number into the charge of an electron, you get this number. It is not going to be exactly this 96,500, rather it will be 96,488, something around that. So, it is rounded off and then we get 96,500 coulomb. So, now you will get this value to be around 0.25 minus volt. Similarly, this is reaction, this is one example. This, let us say example 2. So, we can have example 2 as aluminium. Let us say aluminium 3 plus 3 electron equal to aluminium. Here also mu 0 aluminium in standard state is considered as 0 and mu 0 Al plus 3 plus equal to minus 481,200 joule per mole. So, I can again get the same thing mu 0 Al plus Al minus mu 0 Al 3 plus equal to plus 481,200 equal to minus 3 F E 0 aluminium. So, now every time I am writing ox by rate, that means this is oxidant, this is reductant, this is oxidant, this is reductant. So, now from this we can also get E 0 Al 3 plus aluminium equal to 481,200 by 3 into 96500 would be equal to minus 1.662 volt. So, we can also get like that, we can also get for zinc, where mu 0 zinc solid equal to 0 in standard state and mu 0 zinc plus plus in solution, aqueous solution, it becomes minus 147,030 joule per mole. So, again we get so, this becomes like that we get it. Now, let us see some other thing. For example, if we consider Ag, which is silver, plus E equal to Ag, again mu 0 Ag solid in standard state equal to 0 and mu 0 Ag plus equal to minus 77,120. So, then this is plus, this is plus joule per mole. So, then we get delta 0 equal to minus 77120 equal to minus 1 into F E 0. So, I get volt. So, here I am getting a very positive voltage and we know that hydrogen is E 0 hydrogen is 0 volt. Now, you see from this calculations that pure metals, in case of pure metal, the reduction of ions of pure metal, we can have reduction potential. These are all standard reduction potential. Now, we can also place them with reference to hydrogen electrode. Now, if we try to place all those values, now if I see that this is a particular line and now hydrogen is here, this is in volt unit, this is hydrogen. This is hydrogen. Now, if I try to place nickel in the same scale, then it is minus 0.25, which is E0 nickel plus nickel. Now, if I try to place zinc, which is minus 0.76 E0 zinc plus zinc, and then I can also put Ag, which is plus 0.80 around that, which is around, this is E0 Ag plus Ag. Like that, we can calculate for all the other metals and we can distribute in this particular scale. Now, interestingly, if we have, let us say, as we have seen that zinc, if you put a zinc plate in HCl, we see that hydrogen bubble. Hydrogen bubble formation, and that time our reduction is H2 and oxidation reaction is plus plus. Now, let us see, is there any correlation between this reactions and the kind of scale what we are getting, or kind of distribution of reduction potential or the standard reduction potential in this particular plot, Now, see, this 0 value is lying on top of this minus 0.76 volt, and here also we are seeing that this is cathodic and this is anodic. That means, if we have a connection between these two, I could see that which one is behaving as a noble, which one is behaving as an active element. Now, in this case zinc corrodes. So, that means it becomes active in HCl solution and hydrogen gas evolves. So, this is acting as a noble part in that particular two half cell reactions and the complete cell reactions. Similarly, if we connect these two, we could see that nickel reduction will be, nickel ion reduction would be preferred and zinc would dissolve. So, again I could see that in this particular reaction nickel plus nickel, zinc plus plus. So, I would say this should be written like this. So, here this would be acting as positive, this would be acting as negative if we have unit activities of those ions, of those nickel as well as zinc ions. So, then this would be noble and this would be active component of that particular cell. So, now from this particular, and for example, Ag and zinc, if I connect Ag and zinc, we would also see the similar behavior. That means, Ag would deposit because of the reduction process of Ag plus ion, and zinc would dissolve because of this active nature of zinc, because its reduction potential is way below the reduction potential of zinc plus zinc, Ag plus Ag. Now, like that way, when we distribute all the standard reduction potentials, we call it as standard reduction potential series. And in this, we, in order to construct this, the criteria is activity of metal ion should be 1, metal should be pure. So, and also since this is a standard reduction potential, the temperature 25 degree Celsius and 1 atmosphere. So, this is the criteria to have this series, and in fact we can calculate this potential, this E0, with reference to hydrogen, standard reduction hydrogen potential, rather a standard hydrogen cell. We can measure this, because here the potential E0 H plus H2 is maintained as 0. So, we can calculate this potentials with reference to this. Also we can calculate, once we know the thermodynamic data, that means the chemical potential of ions as well, because the chemical potential of the pure component is considered as 0 if it is a standard state. That means it is in a standard and it is a stable state at 25 degree Celsius and 1 atmosphere pressure. So, this is standard reduction potential series, and this series what information it can give? One information is, one is active and noble part in a cell we can get to know. For example, the example what we have provided, this, even for silver and zinc. For your information, if you start with a silver zinc alloy and then expose it to HCl solution, then you would see that if you start, for example, zinc 75 Ag25, and if you put it in HCl, dilute HCl solution, after some time you will see that the silver, this particle, even if you say start with a particle, small particle, this particle would have several small pores, and those pores, if we analyze this composition again, you would see that zinc has gone down 75% of that composition, initial composition. The zinc concentration would be very low in that remaining porous particle, and silver concentration would increase more than 25%. So, this happens because in this condition, this particular standard reduction potential is pretty high, as well as this one is pretty low, and then if we compare these two reactions, then this zinc plus zinc would corrode, zinc would dissolve, and silver would remain, or silver would deposit back if at all there is silver in the system. And then we have this kind of situation. So, silver would act as a cathode and zinc would act as an anode. Okay. So, the zinc becomes your active component and silver becomes your noble component. So, that information we can definitely get. Now, let us continue with our discussion. Now, we see that in case of pure metal ion reduction, we can calculate standard reduction potential. Now, we have been talking about one reaction, which is O2 plus 2H2O plus 4E equal to 4OH minus. Or we have also mentioned about another reaction 4H plus 4E equal to 2H2. So, these two reactions can happen in aqueous medium when we have dissolved oxygen. Now, in addition to that, depending on the pH, we can have two more reactions in aqueous medium, which is these two. Or we can have H plus 2E equal to H2. So, these four reactions that are important in aqueous medium or the water medium, and we have already talked about these four reactions before, we just mentioned. Now, this is also a reduction process, this is reduction, this is reduction, this is reduction. Now, we can also have standard reduction potential for those reduction processes, and that case definitely in this case, in these two situations, we have to consider again 25 degree Celsius, 1 atmosphere pressure, PO2 should be 1, activity H2O should be 1, activity H plus should be 1. Okay. And here also similarly these three conditions, rather in these three conditions should be prevailing here, and here we have pH2 should be 1, H2 would be 1, activity OH minus would be 1 and activity H plus would be 1. So, then we can get standard reduction potential for these reactions. We have already seen the standard reduction potential for this. We have seen this. Now, let us calculate one of those oxygen reduction, and you see this is 0 oxidation number and that goes to -2. So, it is basically reduction. So, we have to see this particular situation. Now, in this case definitely we can also calculate delta Z 0 equal to mu 0 to H2O minus mu 0 H plus minus mu 0 O2. And then we can equate it to minus NFE0 oxygen, and I can put it like this. So, this is 2. Now, here N equal to 4, E equal to 96500. Now, I can have the value of mu 0 H2O equal to minus 236,964.2 joule per mole. So, then I get delta Z 0 equal to minus 2 into 236,964.2. Now, you see this one is already 0 and this one is also 0 because this is a gas and this is a standard state. So, its value is 0. So, then this equal to minus 4 into 96500 into E0 oxygen to H2O. So, then we get E0 oxygen to H2O equal to 2 into 236,964.2 divided by 2, 4 into 96500. So, it becomes 2 into 2, 964.2 divided by 4. So, it becomes 1.227 volt. So, we can also calculate the standard reduction potential for this reaction. So, this is the value. So, like that we can calculate for other reactions. So, let us stop here. So, we will continue our discussion in our next lecture. Thank you.